Okay, guys, we're going to start this section with giving a little preview of calculus here, and we're going to be discussing two problems that are sort of the motivation for this subject. So I want to start with the first one here, the tangent problem, and I've already gotten a XY plane here, or the first quadrant of it anyways. This works anywhere on the plane, but just for simplicity here, we're going to look at this function here. So let's pretend we have a function here going through the XY plane, and we're going to fix a point P. Let's assume we draw a tangent line. So here's where the name comes from, a tangent line. So if you draw a tangent line to this point P on the function f, when we say a tangent line, we're referring to a line that intersects a curve at a given point, or a specific point. Only one point though. So in this case, we have this point P. And if you wanted to find the slope of this line, if we recall our concepts from pre-calculus, you remember that the slope of a line, you had this nice formula here. Slope of a line is equal to y2 minus y1 over x2 minus x1. And where, x and y were, or x1 comma y1 was the coordinates of the first point, and x2 comma y2 were the coordinates of the second point. So that was easy to do, pretty straightforward to do in pre-calculus if you had 2 points on the line. But we need to have a second point, and the problem here is that we only have 1 point, namely P. So how do we find the slope of this point, of this line going through P if we only have this 1 point? Okay, so if we have our original graph here with our original function with our point P, and we've already determined we can't find the slope of the tangent line with just 1 point. We need a second point. So let's start approximating this. Okay, we can't find it right away, or not, at least not with the algebra that we know. Trace a line that would intersect the function at 2 points. So it goes through P still, but we have a second point here on the function. And let me make sure I mark that point here. So you guys see that point. Let's say we're just going to call it Q here, point Q. So then now we're able to use our nice formula from pre-calculus algebra to find the slope of that line. Now, this line is no longer the tangent line of interest here, but it's what we call a secant line. Secant line intersects this curve through 2 points here. We call this a secant line, but we can start approximating roughly what the slope of a tangent line is by looking at the slope of the secant line. So let me label some things in here. This point P, let's say we have we're going to call that the coordinate x there, right? And the coordinate y for point P would be, since this we label this function to be f of x, and that input is x, so then this y, that output would be f of x, right? So the function evaluated of x. All right, similarly here, if say this Q happens to be, I don't know, just for the purpose here of labeling this distance some constant. So I'm going to call this, let's say this distance is h right here from x to this next point on the horizontal, on the x-axis, right? So let's say this point is x plus h, right? So we're going to get that the y coordinate here, this would be f using the same idea that we did here, f of that input here, which is x plus h. Okay, so let me move this somewhere else here, so it's not confusing there. So we got our f of x plus h. So those are the coordinates of that point P and Q. All right. So here we're going to see that this secant line, even though it's not the same as the tangent line, we can still, try to find the slope. And because we have 2 points instead of 1, so we're able to use this formula here. So I can, let me see, using this formula, I'm going to get that the slope of, and I'm going to call that line PQ here, is going to be equal to, right? Remember, we take that 1 point, or we do the difference of the y. Okay, so let me mark this here with, if we keep going here, and you see form your triangle there, this distance right there would be, wouldn't that be this y minus that y? So we'll have the f of x plus h minus f of x, right? And then this difference in the x would be, so let me go ahead and write here the difference of the y, which again, guys, this is, in your book you might see it as some books have it as delta y over delta x. This symbol delta, the letter delta, Greek letter delta, means just difference between those two. So we have the difference of the y would be, based on using our notation here, would be f of x plus h minus f of x. And all of this will be divided by the difference in the x. Well, if you look at the difference x, remember we said this was h. Also, if you do this minus that, that will give you exactly h, right? Because you do x plus h minus x will cancel out, and you'll get the h there on the bottom. This becomes our slope of the secant line right there. Okay. So we have that. Now we're going to use that. Some of you recognize this already. So I purposely use this h and set it up this way so that you can hopefully identify this from algebra, right? Or from your prerequisite stuff. This is what we call in algebra the difference quotient, right? And you did a lot of algebraic work and simplifying this quotient here. So we're going to go back to that and see how we're going to use this here, right? So that difference quotient that you know of from your algebra course happens to be the slope, in our context here, happens to be the slope of the secant line that going through P and Q. Okay, so again, how does that help us with finding the slope of the tangent line? Well, the tangent line is a completely different line, and they're not going to have the same slope because they don't have the same steepness. But here's the idea. If I move this point Q and I start getting closer, if I move this way in this direction, if I start getting closer and closer, so let's say I move it here and then I move it there, and then as I move this point Q, the secant line is also moving with it, right? You're going to start getting a better and better approximation of the actual tangent line. Remember, the point is to get closer and closer to this point P without having to actually get there. Because as soon as we get to P and we let Q be equal to P, then we no longer have 2 points. We just have 1 point, and then that keeps us from using this slope formula because we need 2 points. Also, looking at this quotient, difference quotient here, remember this h is this distance here. So actually let me mark it over here. This is h, guys. So this h right here, as Q is going to P, as this point Q is getting closer and closer to P, is approaching P, that's the same thing as saying this distance h is actually getting closer and closer to 0, because as this q is moving towards p, this distance is getting smaller and smaller, right? So you're going sort of this way. In other words, it's equivalent to saying h is getting closer, it's smaller, getting smaller and smaller to kind of approaching 0 there. And this word approaching, we're going to use a lot here once we define limits. This is the whole idea. So this was the whole problem here. The tangent problem was how do we find the slope of the tangent line? Well, I don't know from just remember, calculus didn't exist then. So we were trying to figure out how to do it just with the algebra that they knew. But the problem was that you need an extra point there to do that. So they started approximating, right? And this is the way they did it. So we're trying to get the slope, and we can find the slope of the secant line, right? If we have those 2 points. Okay, well, can we approximate the slope of the tangent line by just getting closer and closer? So I have a function, and this is just your typical x squared function, your quadratic function here, and you recognize that with the parabola. And I have here a point, so let me see if I can, you guys see it there. So I have a point here on 1, 1, and let's say this is our P right there. Let's assume this is our Q point, and we're going to start getting closer and closer to Q. To P. You see how the line is changing too, and we can actually zoom in this a little bit more. You start seeing the gap, but we'll still have a secant line here in place. But if we start moving this Q towards P, notice how, right, the line is also changing, and the slope obviously of each one is becoming closer and closer, or is turning into the approximation is becoming a much better approximation to the slope of the tangent line. So, which eventually, I mean, if you let that Q be P, obviously that would be the tangent line, but the point is to always have 2 points, right, to be able to use that quotient, right? So then how can we get the actual slope of the tangent line if we're not allowed to get to actually merge with P, right? Because then we no longer have 2 points. You see that happening right there. So you can right away see just by looking at this that, right, the closer you get, the closer Q gets to P, that second point gets to that first point, the better approximation. So the closer the slope of that secant line would be to the slope of the tangent line. So the closer you get to it, yeah, you get pretty close to what the slope of the tangent line is, but it's never going to be the exact thing. So how do we get the exact thing? So for that, we need something that we're going to use in calculus here, which is called the limit, right? And that's what we're going to define. So that was the motivation of it. Right? How do we actually compute that without ever getting there, right? So that was the motivation for a sort of a branch of calculus called differential calculus, right? Which is we're going to spend most of our time on this first part of calculus 1. Again, our second point gives us a secant line, but I mean, even if you may think that you're almost there, and then you may say, well, why can't that be the slope of the tangent line? And remember, no matter how close you get, you can always get closer to another point, right? Eventually we'll have to zoom in to be able to see that, but even if you think that you're almost there, you can always zoom in more to see that this line is actually crossing the curve twice, 2 points there, a P and a Q. So I can keep getting closer and closer, and even if I think I'm there again, I can always zoom in more, and you could keep doing this forever, right? And space. Right, in space you can keep doing, or in the plane and space you can keep doing this forever. And without ever actually getting there. So we need to have, and that's where we're going to define this limit process that's going to help us compute this. So going back to our formula here for slope, we'll keep this in mind for right now and come back to it. But basically, again, this difference quotient is the slope of the secant line. And as we saw in the simulation there, that as this Q gets closer and closer to B, we'll get a better approximation. The slope of the secant line is getting closer and closer to what the slope of the tangent line would be. But after we see the limit process, we're actually going to find the exact thing. The other problem that I like to discuss is the area problem here. And I don't want to spend too much time on this one because we're going to, in a way, come back to it after we've discussed or develop all the rules for the differential calculus. This second problem gives motivation for the other part of calculus, the other sort of the branch of calculus, which is called integral calculus. We'll do a little bit of it towards the end of the course, and then of course you will develop more tools for it and applications for the integral calculus and the next course, calculus 2. So let's say we have a function here f, and we want to find the area from over or underneath the curve of some function and bounded with the x-axis, let's say in this particular example. How do we find the area underneath the curve, this region right here? When this curve is defined by some function, but and again, this before calculus, mathematicians wonder about, okay, how can we do this? And they didn't have a way to do it algebraically, not in a way where we could find an exact answer, but they started thinking about ways to approximate this area. And again, one of the ways that are the ideas they came up with was, okay, what if we split this region into sections that are easy to compute, areas of. Let's split this interval from A to B into equal sections. Okay, well, let's start with just 2. Let's say we split this right in half, and then we draw a rectangle there, right at the middle, or from the beginning to the first sub-interval. We only have 2 partitions. This is what we call partitions, or 2 divisions of this interval. So we do that, and then from this one here, another. So if you look at these 2 rectangles here, you can see, oh, okay, well, if I have this function, I'm able to compute, and I know this points right here, I'm able to compute the area of this rectangle because, it's just area of the rectangle base times height, right? So I only had to compute, okay, this height is really just a function at A, so I can figure that out if I have f, and obviously this A and B are just some arbitrary numbers. So this distance right here, this width, is half of this length from A to B, right? So and of course this will be the same thing. Now this will have a different height. That would be f of whatever this value is here. So, but the problem with this was that the area is not exact, as you can see, right? The area underneath the curve, you have more area here that is not being covered right there, and then you have more area that is above the area that we're trying to find. So this was an approximation, and then we start applying the idea of, okay, what if we have more partitions, right? So what if I want, instead of having 2 pieces, I have 4. So you can see how, we're still missing some area there, but we were able to chop off or reduce the area that we were overestimating here. This is every time we partition it into more sub-intervals here, we're making the estimation to be a lot better, right? So we start covering now more area. So let's say if we, have two pieces there, and this is just your normal quadratic. I mean, this will work on any function. So let's say, just for the sake of argument here, we want to find the area underneath the curve x squared, f of x equal to x squared, from 0 to 2. Now, you know this parabola from 0. So in other words, this area here from 0 to 2, that's two pieces right there. If I want to go, if I add more, 4, 6, okay, can you see that the more rectangles that I add, my approximation of the area is getting better and better, right? Now, of course, if you were doing this algebraically, you will have to literally add one by one the area of each single rectangle, add them all together, right? And if you want a better approximation, you'll have to have a bunch of these, right? Now, I mean, we can go as high as you want to go. Like, we can do 1,000,000 of this. That would be impractical and inefficient to do by hand, but you see the idea. But no matter how many partitions we get, how many rectangles, we still have an estimation. We have an approximation. It's never the exact thing, right? So then the idea, then again, this makes us think again about the limit process again, and that's where the motivation came from. So again, you may seem like it's starting to cover the whole area, but you can always zoom in, just like we did with the point P and Q, right? Even if it seems like it's almost there, you're actually, every time you zoom in, you're always going to have that gap. Same thing here. Like, even if it starts looking like it's filling all that area, the more you zoom in, you see that, oh, there's still a lot of gaps everywhere, right? And even if I increase the number, it starts getting smaller again, right? Better approximation, but I can still keep zooming in. So the area under the curve, finding that area exactly, gives the motivation for integral calculus. So I want to finish here with just a little chart here. We have now the tangent problem here, right? And then we have the area problem, right? So then basically this tangent problem sort of gave birth to this branch of calculus we call the differential calculus, right? And this second problem here, the area problem, just sort of gave birth to this integral calculus. These two form part of the same topic here. Differential and integral calculus, they'll form part of our subject here of interest. Okay, so this calculus has these two main parts, differential and integral calculus. And we're going to see both of these in this course, but the main bulk of the course would be differential calculus. It will take us some time to build the rules and the applications for differential, and then we'll move on into the integral calculus. I gave you on this section pretty much the two problems. They give the motivation for each one, and they all form part of calculus, but they both, as you saw, to be able to solve it, right? When they got stuck on how to get the exact answer, they are both going to need a tool here that we call the limit process. These two relied on this limit process to be able to, come up with a solution, to be able to understand logically how to get to, in the case of the tangent problem, how to get to the finding the slope of that tangent line, and in the case of the area problem, how to find the actual area, the exact area under the curve of a given function from some point, suppose over an interval. So this limit process is what's going to allow us to not only solve that, but actually extend our knowledge into the subject of calculus, and is going to be a crucial tool to be able to develop all the rules that we'll see.